Now let's say that we have an adiabatic process, and remember that adiabatic means we have no thermal contact with an environment. Adiabatic process implies Q is equal to 0. This could be, for example, slow expansion of a gas in a thermally insulated vessel. And in this process, when I write the first law of thermodynamics, I can remind you that this is going to be the heat added plus the work done on the system. Because the heat added is 0, the change in the internal energy is achieved by doing work on the system. If I write this in differential form, a small change in the internal energy will be equal to minus P dV. That's the amount of work that we do in a quasi-static process. So the change in the internal energy can always be achieved using an isovolumetric process. So I can always write dE internal could be done using this isovolumetric process by NCV delta T. This is the isovolumetric version, so that there is no work done on the system. Now, if the same internal energy change is achieved using the adiabatic process, then I have NCV dt must be equal to minus P dV. So dt is equal to minus P dV divided by NCV. Now, since this is an ideal gas law applies. Ideal gas law applies. So I'm going to have PV is equal to nRT. If I take the differential version of this, PdV plus VdP is equal to nR dt, because I'm not changing the number of moles of gas. And I find that dt is minus pdv divided by ncv, so I have pdv plus vdp is equal to nr minus pdv divided by ncv. So the n's cancel. So this is going to be minus r over cv p dv. And remember, r is equal to cp minus cv. So pdv plus vdp is equal to minus cp minus cv over cv pdv, and cp minus cp divided by cv was defined as gamma. So this is going to be minus gamma minus 1 p dv. So if I take this to the left hand side, I have p dv plus gamma minus 1 p dv plus vdp is equal to 0. Therefore, I find that gamma times p dv plus vdp is equal to 0. If I integrate this from initial state to final state, I will find, or before I do this integration, I have to do separation of variables. So let's rewrite this. Gamma times p dv plus vdp is 0. And I'm going to divide this equation with pressure times volume in order to have only one type of variable in one term. So this is going to give me gamma dv over v plus dp over p is equal to 0, which I'm going to integrate from the initial state to the final state. So I find gamma ln v final over v initial plus ln P final over P initial is equal to 0. So if I call V final V, P final P, and gamma times ln V initial and gamma times ln P initial, so this will be gamma ln V plus ln P minus gamma ln V initial minus ln P initial is equal to 0. So I will find that at the end, this is going to give me gamma times ln V plus ln P is equal to some constant, depending on the initial conditions here. So I will find that ln V to gamma plus ln P is a constant, which means ln PV to gamma is a constant, or PV to gamma is a constant. Therefore, in an adiabatic process, you will have initial state pressure times volume to gamma is equal to final state pressure times volume to gamma. So this will be true for an adiabatic process. And furthermore, if you write PV is equal to nRT, so P initial V initial times V initial to gamma minus 1 is nRT initial V initial to gamma minus 1, and this must be equal to P final V final to gamma minus 1. So this will give me nRT initial V initial to gamma minus 1 is nRT final V final to gamma minus 1, and R's will cancel, so I will find that I also have temperature, initial volume to gamma minus 1 is final temperature, final volume to gamma minus 1. So there are two ways I can write this equation, either using pressure and volume or temperature and volume. So basically, I have this relationship between pressure and volume and temperature and volume for an adiabatic process. Now, if you look at the way pressure varies as a function of volume, in order to compare these three different types of processes, for the isobaric process, pressure is a constant. For an isothermal process, you have pressure is equal to nRT over V. For the adiabatic process, pressure is a constant divided by V to the power gamma, where gamma is Cp over Cv and it's greater than 1. For an isovolumetric process, you have volume is a constant. V is a constant. So this basically summarizes the different types of PV curves you can have depending on the type of process we use.